Thank you so much for inviting me. It's such a pleasure to be talking about these things here in my own department, and it's so cool to see how many interesting things are happening right here. So I'm going to talk about keeping AI under control with mechanistic interpretability, and in particular, how I think we physicists have a great opportunity to help with this. So first of all, why might we want to keep AI under control? Well, obviously, as we've heard this morning, because it's getting more and more powerful. We've all seen this paper from Microsoft. It's arguing that the GPT-4 is already showing sparks of artificial general intelligence. Here is Joshua Bengio.
Now reached the point where there are AI systems that can fool humans, meaning they can pass the Turing test.
So you can debate whether or not GPT-4 passes the Turing test, but Joshua Bengio should certainly get a vote in that debate, since he's one of the Turing Award winners, the equivalent of the Nobel Prize for AI. And this growth and progress is obviously also, as you know, started freaking a lot of people out. Here we have his Turing Award co-winner, Jeff Hinton. I'm not sure if the audio is actually going out. Is it?
Are we close to the computers coming up with their own ideas for improving themselves?
Yes, we might be.
And then it could just go.
That's an issue, right? We have to think hard about how to control that.
Yeah, can we?
We don't know. We haven't been there yet, but we can try.
Okay, that seems kind of concerning.
Yes.
And then piling on Sam Altman, CEO of OpenAI, that of course has given us ChatGPT and GPT-4, had this to say.
And the bad case, and I think this is like important to say, is like lights out for all of us.
Lights out for all of us. Doesn't sound so great. And of course, then we had a bunch of us who called for a pause and an open letter, and then we had, shortly after that, this bunch of AI researchers talking about how this poses a risk of extinction, which is all over the news. Specifically, it was the shortest open letter I've ever read. It had just one sentence. Mitigating the risk of extinction from AI should be a global priority alongside other societal scale risks such as pandemics and nuclear war. So basically, the whole point of this was just that it mainstreamed the idea that, hey, maybe we could get wiped out, so we really should keep it under control. And the most interesting thing here, I think, is who signed it. You have not only top academic researchers who don't have a financial conflict of interest, people like Jeff Hinton, Joshua Bengio, but you also have the CEOs here, Demis Hassabis from Google DeepMind, Sam Altman again, Daria Amadei, etc. So a lot of reasons why we should keep AI under control. How can we help? I feel that, first of all, we obviously should. And Peter, earlier this morning, gave a really great example of how I think we really can help by opening up the black box and getting to a place where we're not just using ever more powerful systems that we don't understand, but where we're instead able to understand them better. This has always been the tradition in physics when we work with powerful things. If you want to get a rocket to the moon, you don't just treat it as a black box and you fire it. That one went a little too far to the left. Let's aim a little farther to the right next time. No, what you do is you figure out the laws you figure out Einstein's laws of gravitation, you figure out thermodynamics, etc., and then you can be much more confident that you're going to control what you build. So this is actually a field which has gained a lot of momentum quite recently. It's a very small field still. It's known by the nerdy name of mechanistic interpretability. To give you an idea of how small it is, if you compare it with neuroscience, and you think of this as artificial neuroscience, neuroscience is a huge field, of course. And look how few people there are here at MIT at this conference that I organized just 2 months ago. This was the biggest conference by far in this little nascent field, okay? So that's the bad news. There's very few people working on it. But the good news is, even though there are so few, there's already been a lot of progress, remarkable progress. I would say more progress in this field than in all of big neuroscience in the last year. And why is that? It's because here you have a huge advantage over ordinary neuroscience in that, first of all, to study the brain with 10 to the 11 neurons, you have a hard time reading out more than 1,000 at a time. You need to get IRB approval for all sorts of ethics reasons and so on. Here, you can read out every single neuron all the time. You can also get all the synaptic weights. You don't even have to go to the IRB either. And you can use all these traditional techniques where you actually mess with the system and see what happens that we love to do in physics. And I think there are 3 levels of ambition that can motivate you to want to work on mechanistic interpretability, which is, of course, what I'm trying to do here, to encourage you to work more on this. The goal of it is, the first lowest ambition level is just when you train a black box neural network on some data to do some cool stuff, to understand well enough that you can diagnose its trustworthiness, make some assessment of how much you should trust it. That's already useful. Second level of ambition, if you take it up a notch, is to understand it so well that you can improve its trustworthiness. And the ultimate level of ambition, and we are very ambitious here at MIT, is to understand it so well that you can guarantee trustworthiness. We have a lot of work at MIT on formal verification, where you do mathematical proofs that a code is going to do what you want it to do. Proof-carrying code is a popular science topic in computer security, where it's a little bit like a virus checker in reverse. A virus checker will refuse to run your code if it can prove that it's harmful. Here, instead, the operating system says to the code, give me a proof that you're going to do what you say you're going to do. And if the code can't present the proof that the operating system can check, it won't run it. It's hopeless to come up with rigorous proofs for neural networks, because it's like trying to prove things about spaghetti. But the vision here is if you can use AI to actually mechanistically extract out the knowledge that's been learned, you can re-implement it in some other kind of architecture which isn't a neural network, which really lends itself to formal verification. If we can pull off this moonshot, then we can trust systems much more intelligent than us, because no matter how smart they are, they can't do the impossible. So, in my group, we've been having a lot of fun working on extracting learned knowledge from the black box in the mechanistic interpretability spirit. You heard, for example, my grad student, Eric Michaud, talk about this quantum thing recently. And I think this is an example of something which is very encouraging, because if this quantum hypothesis is true, you can do a divide and conquer. You don't have to understand the whole neural network all at once. But you can look at discrete quantity that's learned and study them separately, much like we physicists don't try to understand the status center all at once. First, we try to understand the individual atoms that it's made of, and then we go work our way up to solid-state physics and so on. Also reminds me a little bit of Minsky's Society of Minds, where you have many different systems working together to provide very powerful things. I'm not going to try to give a full summary of all the cool stuff that went down at this conference, but I can share, there's a website where we have all the talks on YouTube if anyone wants to watch them later. But I want to just give you a little more nerd flavor of how tools that many of you here know as physicists are very relevant to this. Things like phase transitions, for example. So we already heard a beautiful talk by Jacob Andreas about knowledge representations. There's been a lot of progress on figuring out how large language models represent knowledge, how they know that the Eiffel Tower is in Paris, and how you can change the weights so that it thinks it's in Rome, et cetera, et cetera. We did a study on algorithmic data sets where we found phase transitions. So if you try to make the machine learning learn a giant multiplication table, this could be for some arbitrary group operation, so something more interesting than standard multiplication. Then, if there's any sort of structure here, if this operation is, for example, commutative, then you only really need the training data for about half of the entries, and you can figure out the other half. because it's a symmetric matrix. If it's also associative, then you need even less, etc. So as soon as the machine learning discovers some sort of structure, it might learn to generalize. Here's a simple example, addition modulo 59. We train a neural network to do this. We don't give it the inputs as numbers. We just give it each of the numbers from 0 to 58 as a symbol. So it doesn't have any idea that they should be thought of as numbers, and it represents them by embedding them in some internal space. And then we find that exactly at the moment when it learns to generalize to unseen examples, there's a phase transition in how it represents in the internal space. We find that it was in a high-dimensional space, but everything collapses to a two-dimensional hyperplane, I'm showing you here, in a circle. Boom. That's, of course, exactly like the way we do addition modulo 12 when we look at a clock, right? So it finds a representation where it's actually adding up angles, which automatically captures in this case, the commutativity and the associativity. And I suspect this might be a general thing that happens in learning language and other things also, that it comes up with a very clever representation that is such that it geometrically encompasses a lot of the key properties that lets it generalize. We do a lot of phase transition experiments also. We tweak various properties of the neural network and see that sometimes so there's one region of, if you think of this being water, you could have pressure and temperature on your phase diagram, but here there are various other nerdy machine learning parameters. And you get these phase transition boundaries between where it just learns properly, where it can generalize, where it fails to generalize and it never learns anything, or where it just overfits. This is for the example of just doing regular addition. So you see it learns to put the symbols on a line rather than a circle in the cases where it works out. So I want to leave a little bit of time for questions, but the bottom line I would like you to take away from all this is, I think it's too pessimistic to say, oh, we're forever just going to be stuck with these black boxes that we can never understand. Of course, if we convince ourselves that it's impossible, we're going to fail. That's the best recipe for failure. I think it's quite possible that we really can understand enough about very powerful AI systems that we can have very powerful AI systems that are provably safe. And physicists can really help a lot because we have a much higher bar for what we mean by understanding things than a lot of our colleagues in other fields. And we also have a lot of really great tools. We love studying nonlinear dynamical systems. We love studying phase transitions and so many other things which are turning out to be key in doing this kind of progress. So if anyone is interested in collaborating or learning more about mechanistic interpretability and basically studying the learning and execution of neural networks as just yet another cool physical system to try to understand, just reach out to me and let's talk. Thank you.
All right, thank you very much. Does anyone have questions? I actually have one to start with. So just sort of you explaining in these last few slides, a lot of the themes sort of seem to be applying like the laws of thermodynamics and other physical laws to these systems. And the parallel I thought of is the field of biophysics also sort of emerged out of this, right? Applying physical laws to systems that were considered too complex to understand before we really thought about it carefully. Is there any sort of emerging field like that in the area of AI or understanding neural networks, other than that little conference you just mentioned? Or is that really all that's there right now?
There's so much room for there to really be an emerging field like this, and I invite all of you, to help build it. It's obviously a field which is not only very much needed, but it's just so interesting. There have been so many times in recent months when I read a new paper by someone else about this, and I'm like, oh, this is so beautiful. Another way to think about this is I always tell my students that when they pick tasks to work on, they should look for areas where there's more data, where experiment is ahead of theory. That's the best place to do theoretical work. And that's exactly what we have here, right? If you train some system like GPT-4 to do super interesting things, or use Llama 2 that just came out where you have all the parameters, it's an incredibly interesting system. You can get massive amounts of data, and we have the most fundamental things we don't understand. It's just like when the LHC turns on, or when you first launched the Hubble Space Telescope, or the WMAP satellite or something like that. You have a massive amount of data, really cool basic questions. It's the most fun domain to do physics in, and yeah, let's build a field around it.
Thank you. Yeah, we've got a question up there.
Hi, Professor Tegmark. I was wondering, so first amazing talk, I love the concept, but I was wondering if it is possible that this approach might not oversee, but miss situations in which the language model actually performs very well, not in a sort of like a concise region, like a phase region on parameter space, but rather like in small blobs all around, because like in most physical systems, we have a lot of parameters that will have phases, and the phases are mostly concise in regions of n dimensions or whatever, and then there are phase transitions, which is the concept here. But it is also, like, since this is not necessarily a physical system, maybe there might be a situation in which the best way that it performs is in specific combinations of parameters. There are like points or little blobs around. I don't know if my question went through.
Yeah, it's a good question. I think I need to explain better. I think my proposal is actually more radical than maybe I could properly explain. I think we should never put something we don't understand, like GPT-4, in charge of the MIT nuclear reactor or any high-stakes systems. I think we should use these black box systems to discover amazing knowledge and discover patterns in data, and then we should extract, not stop there and just connect it to the nuclear weapon system or whatever, but we should instead develop other AI techniques to extract out the knowledge that they've learned and re-implement them in something else, right? So to take a physics metaphor again, that's like Galileo, when he was 4 years old, if his daddy threw him a ball, he'd catch it, because his black box neural network had gotten really good at predicting the trajectory. Now, then he got older, and he's like, wait a minute, these trajectories always have the same shape. It's a parabola, y equals x squared, and so on. And when we send the rocket to the moon, right, we don't put a human there to like make poorly understood decisions. We actually have extracted out the knowledge and written the Python code or something else that we can verify. I think the real power, I think we need to let go of, stop putting an equal sign between large language models and AI. We've had radically different ideas of what AI should be. First, we thought about it in the von Neumann paradigm of computation. Now we're thinking about LLMs. We can think of other ones in the future. What's really amazing about neural networks, in my opinion, is not their ability to execute computation at runtime. They're just another massively parallel computational system, and there are plenty of other ones too that are easier to formally verify. Where they really shine is in their ability to discover patterns in data, to learn, right? And let's use and continue using them for that. You could even imagine an incredibly powerful AI that is just allowed to learn, but is not allowed to act back on the world in any way. And then you use other systems to extract out what it's learned, and you implement that knowledge into some system that you can provably trust. This, to me, is the path forward that's really safe. And maybe there'll still be some kind of stuff which is so complicated we can't prove that it's going to do what we want. So let's not use those things until we can prove them, because I'm confident that the set of stuff that can be made provably safe is vastly more powerful and useful and inspiring than anything we have now. So why should we risk losing control when we can do so much more first in a provably safe way?
Thank you. I'll keep my question short. So for your phase transition example, is it just an empirical observation, or do you have a theoretical model like you do in physics?
Right now, it's mainly a theoretical observation, and actually we have seen many examples of phase transitions cropping up in machine learning, and so have many other authors. I'm so confident that there is the beautiful theory out there to be discovered, the sort of unified theory of phase transitions in learning, and maybe you're going to be the one to first formulate it. I don't think it's a coincidence that these things keep happening like this, but this gives you all an example of how basic physics-like questions there are out there that are still unanswered, where we have massive amounts of data as clues, to guide us towards them.
Thank you.
And I think we probably even going to discover. We will probably discover at some point in the future even a very deep unification relationship or duality between thermodynamics and learning dynamics is the hunch I have.